And we'll close our quantum physics unit here with perhaps the strangest experiment in all of physics. Um, and a little discussion of where that strange experiment leads us, which is towards uncertainty. So we're going to go back to our double slit experiment. And in the double slit experiment, we saw when you shine uh, coherent light through an interference diffraction or through a diffraction grating, you got an interference pattern. Okay. What if we reduce the intensity of the light so only one photon is moving towards the slit at a time? So what happens if we, instead of shining a bright light and getting the diffraction pattern, what if we throw a photon at a diffraction pattern, and then so another photon and another photon, or in this case, an electron? It turns out that the path of the photon is completely unpredictable. If I throw one of them at the diffraction grating, you don't know where it's going to hit the screen. It'll hit the screen, but you don't know where. And so let's say I throw 40 of these particles, either photons or electrons. You get the same effect. You get a pattern that starts to look like this. And you say, well, that's kind of random, but you start to see that they're mostly landing in these lines here. If you keep throwing them, you start to see that pattern emerge, right? Here's what our diffraction pattern looks like. Okay. And here's what happens when I've thrown 2,000 particles through our diffraction grating. What's strange about that? Well, the particles follow a probability distribution. In other words, what that means is statistically here, what's happening here is there are more photons hitting here and here than they are down here. And the same thing happens when you throw them one at a time. What's weird about that is that when we talked about this, we explained it as an interference of waves, right? We had two slots or multiple slots. A wave going through one slot interfered with another slot and created these, when those waves were in phase, you get a high intensity. When they were out of phase, you get low intensity. But here, we're just talking about one photon at a time. What are they interfering with? How do these photons that are going through these diffraction gratings individually know that they're supposed to follow some kind of probability distribution? That's really odd. Does the photon somehow go through both slits and interfere with itself? How does it know if it goes through one slit? How does it know where the other slit is? It's a great mystery. So let's do some experimenting. We want to know, well, which slot is it going through? We'll put a detector at both slits, right? So we know when a photon's going to go, so we can tell at least which slit the photon's going through. Okay. If we do that, it doesn't go through both slits. So one of our suppositions is maybe the photon goes through both slits, and that means that it's interfering with itself in some way. That's not the case. Okay, so it always goes, we can detect it through one, but it doesn't set off both detectors. But if we keep those detectors there, it no longer makes the diffraction pattern. And that's where things get like spooky weird. If you turn the detector off, the electron's going back to making a double slit pattern. So no detectors. I throw these photons at my diffraction grating, and I get a nice diffraction pattern over time. Turn on the detectors, the diffraction pattern disappears. We know which slit the photon goes through, and it acts as if it's only going through that one slot. Then we turn the detectors back off, and you go back to getting this probability distribution. It's as if the photons know they're being detected and don't want us to figure out what is going on. But that doesn't make any sense, right? We as much as we'd like to, we can't give these electrons human characteristics. So what do we do? Uh, we sort of wonder at the world, right? There's not, we don't have a great explanation of this, and so, and you think I'm being ignorant because I don't know the answer to this. I'm going to refer to Richard Feynman here, who's probably the most famous American physicist of the 20th century. And this is what he said in one of his famous lectures. He said the double slit experiment, what we've just been talking about, has in it the heart of quantum mechanics. In reality, it contains the only mystery. Nobody can give you a deeper explanation of this phenomenon than I have given. That is a description of it. And so again here, I talked about this with magnetism here. There's a point in physics where the wise don't have good answers. We can describe what is happening physically, but we don't really have a good way of saying why these photons are behaving like they are. And again, that's where our metaphors fail us. Our explanations of physical phenomenon are metaphors. We explain something we don't see by comparing it to something that we do see. There is nothing that behaves the way that these photons behave in the world that we see. And so our metaphors basically kind of collapse for us. We don't have a good way of explaining these results. But we can make some observations, and they're not small observations. They're really important ones. One is that measurement affects the system being observed. This is true at any level, at the Newtonian level or the quantum level, but it's particularly true at the quantum level. If we try to follow an electron, any way that we can use to detect where that electron is going to change that electron. It has to absorb some photons, it has to hit a detector of some sort, and that is going to change the way that it's acting. And so that's one of those things. When we detect an electron in the double slit experiment, we're clearly changing that electron or that photon, and that's changing its behavior. And so it becomes impossible for us to observe that without changing the situation that we're observing. The second thing that's important is that the particle wave duality is our best tool for understanding quantum behavior. So what that means is that we have to keep two different ways of understanding light in our head at the same time. It behaves like a wave and it behaves like a particle. Neither of those is sufficient on its own. Both are wrong in particular applications. And so we need to have them both as a way to talk about. I love this quote from one physicist when asked whether a photon was a particle or a wave, said this: "A photon is what is detected by my photon detector." Which, what does that mean? It means we just don't know exactly what a photon is. We know that we're detecting something, that there's a bit of energy that we're able to say passed here or was here at a particular moment. But beyond that, our understanding fails. It's beyond our ken, as we sometimes say. Which is a great phrase. If you ever want to say something's beyond your understanding, say it's beyond your ken. The last implication is what is called the uncertainty principle, or the Heisenberg uncertainty principle, which if you watched I'm blanking on it. The drug dealing chemistry teacher who called himself Heisenberg. Um, may sound familiar. So what is the Heisenberg uncertainty principle is? The heart of it is that it's impossible to measure the velocity and position of a quantum particle at the same time. Uh, and that the strange thing about this is that we want to say, oh, you mean we don't have the tools for it. It's not that we don't have the tools, right? It's not hard to do. It is literally impossible. And this is the theorem, right? It is literally impossible to know where it is and how it's moving at the same time. Okay, if we want to write the Heisenberg uncertainty principle mathematically, it looks like this. And these terms are delta x here. The delta we usually use as change. Here it means uncertainty. So the uncertainty in x times the uncertainty in momentum, so position and momentum, so we can think of this as our velocity term, is always greater than equal than Planck's constant divided by 4 pi. So this is a constant over here. It's a very small constant, right? H is tiny, and we're dividing it by 4 pi. So this is small, but this term can't be 0, right? What does that mean? Well, it means that neither of these can be 0, right? Because that product would be 0. And it also means that as I get a more exact picture of where a particle is, say an electron, I lose my certainty about how fast it's going and in which direction. Okay, and as I figure out its momentum, which direction it's going and how fast, I lose certainty about my position. So I can know one of these very accurately, but then it means that the other one becomes much less certain, and my knowledge of its position or velocity changes. And so that's the mathematical. This is a physical principle, right? This is like a law of conservation. This is physically true, and that means that our knowledge of the quantum world is always going to be partial, which is a big idea. Okay. Unfortunately, we don't have to do the math to figure out where this came from, but it's important to know that idea that our knowledge of the quantum world is partial. And that's the Heisenberg uncertainty principle.